Last time we were able to understand what delta G is. It's Gibbs free energy, and it is using delta H and delta S together to determine whether a system or a reaction will be spontaneous or not spontaneous. We found out if it were negative delta G, it's spontaneous, it gives off energy. If it were positive, it's non-spontaneous, it's going to take energy. Okay, so here's the problem. The Haber process is a reaction that makes ammonia. Okay, and here's the reaction. Assume that delta H for this reaction does not change with temperature. Predict the direction in which delta G for this reaction changes with increasing temperature. Okay, so let's look at this. They want to see how delta G changes. Okay, first I have to predict delta H. Do I have any idea what the delta H is here? I really don't have an idea. They didn't tell us whether it's endo or exo. I don't even know if it's positive or negative. Okay. Do we know what the delta S is? Is it positive or negative? Okay, they're all gases. Pause the video and try to figure it out yourself. Okay, so they're all gases. So you count the moles of gas. So you have 4 moles of gas on this side, and you have 2 moles here. So it becomes more ordered. So that means it's negative delta S. Okay, so this value right here is negative. Okay, that's all we know. It says, predict the direction in which delta G for this reaction changes with increasing temperature. So temperature is right here. And increasing the temperature only changes delta S anyway. So we don't really care about delta H in this case, just for predicting. Okay, so what do you think will happen? If T goes up, this whole value becomes what? Negative and a negative makes a positive number, which means this whole term is going to cause delta G to be more positive. So if you increase the temperature, right, this whole term gets bigger, positive number. The bigger and bigger this gets, you're multiplying it by that, it gets a bigger positive, and the more positive this is, which means it is non-spontaneous. It's bad. So what this means is that if you increase temp, delta G is more positive, which means you're not getting free energy, you are putting it in, okay? You have to put energy into this thing to make it happen. So it's bad. Sad face forever. Okay, let's do the other scenario. Okay, delta G equals delta H minus T delta S. Okay, we know the same thing. This is negative T. Delta S is still negative, of course, because it's becoming more ordered, so it's negative. If this is a small negative number, if temperature gets smaller, it gets colder and colder, that means negative and a negative. This is the smallest. You get a small positive number. Make it a small plus. A small plus will make this into a small plus, which means if it's cold, this value will be smaller, and this term, entropy term, will be more plus. So if it's cold, it is good. It's better. So let's test it. So the formula is delta G equals delta H minus T delta S. All we have to do is plug it in. Delta H. For this reaction, what you need to do is look at the thermodynamic chart. You're going to look at this right here and going to do products minus reactants. To get delta S, you're going to do products minus reactants. Okay, I did that for you ahead of time to save space here and time also. I got my delta H to be negative 92.38 kilojoules per mole reaction, which I'm not writing right now. Negative 92.38 kilojoules. Okay, minus the temperature is at 25 C, which is 298 K. Okay, 298 K. And delta S is given here. So when you do the math for the delta S, it is in J over mole K. So I got J over mole K, mole reaction K, right? Because I multiplied it by moles. So what I'm going to do is change this to, I have to change it to Kj to make them, so I can put them in the same formula. So I'm going to get 0.1983 kilojoules over K. This cancels, so you get kilojoules over K, right? So that goes right here. Point 1983 kilojoules over K. That's a 9.1983. Okay, so the K's will cancel here, as you can see. This cancels with this. You're going to end up with a unit of kilojoules. Okay, if you do this math, I got negative 33.29. Okay, let me verify that really quickly. Okay, so I found my error. This number is a negative number, which makes this negative, and so the math should work now. Okay, so this is at 25 degrees Celsius. Okay, so this is when it's cold. When it's cold, you get some free energy and you are happy. Okay, because you get free energy right here, negative delta G. And if you were to put the unit per mole reaction, you can just put per mole of this whole reaction, okay? That's what that means. So let's try it again here. Delta H is the same one, negative 92.38. We'll use a different color. Kilojoules minus, now the temperature is 500 plus 273, that is 773. Okay, it's hot, 773 K. All right, and this number is negative, oh, this is a negative number, 0.1983. So what that high temperature is doing is exaggerating this value. It's exaggerating how it's very ordered here, right? Kilojoules per K. So again, the K's cancel here and here. When you do this math, you're going to get positive 60.91. The units are in kilojoules, and you can add in mole of the reaction. Okay, let me just verify that answer here. Okay, so that's right. So what this means is this is when it's hot. When it's hot, you don't get free energy. You have to put energy in. So this is not spontaneous. This is spontaneous right here when energy is given out. And that is because it's very hot. Like I said here, the T is going up and it's making this entropy term more positive, which made this more positive right here.